Okay. Welcome everyone. I'm gonna remove that real quick. Welcome everyone to this quick lecture. Should take about 20 minutes is the expected time. So mass flow. So mass flow is complicated. It has a lot of variables that can go into what your mass flow ends up being. And there's a lot of information online and also like a dearth of information online simultaneously on how to actually compute mass flow for various systems. So I want this lecture to clear up for a lot of people in this team how we calculate it, how we measure it, and all that stuff. So okay. So mass flow, it's pretty self-explanatory. Mass flow is caused by a difference in pressure between 2 points. So if you have a vessel that's pressurized to a high volume, or to a high PSI, then you have it going to ambient, mass will flow, the liquid or gas will flow from vessel out to ambient. Fluid will not flow without a difference in pressure. The difference in pressure is what causes mass flow, and on top of that, the difference in pressure between those 2 points scales with mass flow for the most part. A few definitions. So incompressible fluids. Incompressible fluids are going to be your liquids. So these have densities which do not vary based on pressure. And compressible fluids are gases. So their density does vary based on pressure. These differences essentially mean that you calculate the mass flow for these two types of fluids completely differently. So you've got to understand what you're dealing with before you can calculate it. Definitions more. So pressure drop. Pressure drop is the difference between upstream and downstream pressure. I'll be saying pressure drop a lot, and that's what it means. So upstream, you'll have a higher pressure. Downstream, you'll have a lower pressure always. PSIA versus PSIG. So PSI, if you're taking thermo, you'll probably know what the difference is, but essentially you have absolute and gauge pressure. Gauge pressure is what our pressure gauges measure. It's measured as a reference to ambient pressure. So a pressure gauge in my hand right now would measure 0 PSI, but an absolute pressure gauge would measure 14.7 PSI, or whatever the pressure in this room is. Because the PSI absolute is measured with reference to vacuum. It's also important to understand that difference because when you're calculating mass and volume, you want to use absolute, but whenever you're using like typical difference in pressure or you're dealing with pressure gauges or your data, it'll be in gauge. More definitions. So lines are what we call any series of tubes and fittings. And a tube is just a cylinder. I say tube right now because we use tubes, but you can also have pipes, and you'll find information for pipes online a lot. But we use tubes in this club, so I'm just going to call it a tube. And we have fittings as well. Then we also, John edited this and put in this copy pasta that I made about the pipe one. And then it got like a bunch of likes on Twitter from another dude who posted it. So it was funny. Anyway, fittings it's essentially considered an infinitesimal point. And this infinitesimal point has a geometry associated with it and a flow coefficient associated with it. And I'll talk about how we calculate stuff relating to fittings later. All right, K, CV, and CD. You'll hear these three values a lot whenever you're looking up information online or researching. It's important to understand what the difference is so that you don't get them mixed up, as well as you understand how they can and cannot be applied. CV is the one you'll see a lot if you're looking at parts online. Every part that has a fluid going through it, the manufacturer will give you a CV. And so CV is pretty universal in that regard. It's also dimensionless, which means you can apply it to any kind of tubing size and it'll work the same way. If you work with metric at all, it'll be kV, and there's just a simple conversion factor between kV and CD. CD is discharge coefficient. So discharge coefficient is non-dimensional once again, very similar to CD or CV, but it's used in regards to how we characterize fittings and systems. So CD can apply to a lot of things. It can apply to a fitting in a tube system. Typically, it applies to just a fitting system. And you can find CD information online. So if you have a geometry that you know, you can look up research papers or textbooks, and they will have CD values for those geometries. K is a loss coefficient or resistance coefficient. K is used very often in industry in regards to chemical engineers, but also we use K in order to calculate our pressure drop. We convert our CV, our CD, our tube losses to K values. I'll talk about that more later as well. All right, so first mass flow step is incompressible mass flow over a fitting or an orifice or whatever. So this is the basic equation that you will see online for mass flow. And it's essentially useless. And so I say this because we do not use it. We use an alternate. Essentially, the reason it's essentially useless is because the CD value is fuzzy. Like I said, in order to find a CD value, you have to look it up online to find a rough geometry. And on top of that, for any known geometry that we do have like fittings or whatever, we'll use a fluids library online to get the value. However, what it is useful for is characterizing an incompressible flow fitting. So if you have a orifice plate or a valve, and you are trying to characterize that valve for your own purposes, you would use a CD to characterize it. And you can use that relationship, A square root 2 rho delta P, to find flow rates. Then we have the Darcy-Weisbach equation. So this one is for finding pressure drop over the length of a tube. This one's used quite often in industry. You have the Darcy friction factor, and the Darcy friction factor is a factor which is correlated to the friction of the tube, but it's also correlated to a lot of different things. I linked the Wikipedia online for this because Darcy-Weisbach is one of the more researched pressure drop calculations. And this friction factor can vary based on a lot of factors on your system. It can vary based on what your flow regime is, laminar, turbulence, and a bunch of different factors that you can find online. And here's what you actually do. So those are fun equations, but you rarely use those. What you actually do is you use the Python fluids library. So the Python fluids library, essentially, you start with a target mass flow. You set your fluid properties, so what your fluid is. Then along that system, you have a fitting and a tube. So for fittings, the fluids library can generate a dimensionalized K value. And using that K value, you can calculate the pressure drop over all of your fittings. Similarly, it does the same thing with tubes. Tubes have an associated pressure drop, which are calculated through the fluids library. After you add all the pressure drops together, you get your total pressure drop. Note that in this solution, you have mass flow to determine a pressure drop. In real life, it's the other way around. Your pressure drop determines your mass flow. So if you want to determine what your mass flow is for a given pressure drop, you have to iterate over many mass flows and just draw a graph to see where it intercepts, and you got your actual mass flow. And this is just an expansion. So essentially what the fluids library does. You have a geometry, and it's linked here, which is again on the PowerPoint and the Confluence. You have a geometry, and it returns a K value for that geometry. So this is just one, but there are dozens of geometries which the fluids library has. And and you can tailor it to your needs. So you just input a geometry, it outputs a K value. Pretty simple. Geometry's code. So for an incompressible fluid, we use Geometry's code to calculate the pressure drop, which is linked there. And a reminder that pressure drop determines mass flow. I don't know, I wrote that like a bunch of times, but it's important. So, all right, that's it for incompressible fluids. That's all your liquids. That's how you do that. For gases, it's more complicated. Because if you've taken compressible flow or if you haven't taken compressible flow, it's a lot more complicated than Bernoulli's equation. And the key characteristic to compressible flow is understanding choked flow. So choked flow dictates that if your flow is choked, then a decrease in the downstream pressure will not cause a change to your mass flow. However, if you have choked flow and you increase your upstream pressure, there will be an increase in mass flow. I'll explain more why that is later, but the key to understanding when choked flow happens is this equation. So P1 over P2, upstream minus over downstream, times this factor, which is a function of your specific heat, or ratio of specific heats. And if it's greater than 1, you have choked flow. What this equation says is if your flow is supersonic, you have choked flow. The choked flow condition occurs whenever your flow transitions from subsonic to sonic. Your flow, unless you have a perfect isentropic expansion, such as the case in an engine, will not accelerate past Mach 1. And for that reason, you essentially hit like a roadblock. Like you can't shove any more mass through there, no matter how much you decrease the downstream pressure, because it's sonic at that condition. And where will it choke? Everywhere. But let's figure out how to determine the flow rate through that orifice or whatever fitting you have. So these equations are very important. I recommend you save them somewhere or save this PowerPoint, as these 4 equations are very useful. And across how they work is essentially across any single flow constriction, your mass flow can be calculated with these equations. So essentially how this equation works is you have this first value right here, which is the same as the previous slide. It determines if the flow is going to be sonic. If it is, then you check something else, which I forget, and then it gives you your Mach number. Oh, I think it's just the Mach number equation. Yeah, so essentially it just checks if your flow is choked, checks if it's sonic, and if it's subsonic, then you can go through these equations, get your mass flow. If it's sonic, Mach equals 1, then you can just plug m equals 1 for the rest of these. We have a correction factor here, gamma, and you can calculate your mass flux and mass flow. And with this equation, it's also can become evident why an increase in upstream pressure causes an increase in mass flow, while a decrease in downstream pressure does not cause an increase in mass flow. As pressure 2, all that pressure 2 is ever used for is checking if the flow is sonic. I should change that to P1, but whatever. This is P1. I will change that and then re-upload the PowerPoint. This mass flux condition, if you increase your upstream pressure, then you will get a higher mass flow as you have more mass packed into a smaller volume. What choke flow dictates is that you can only have so much volume travel through that orifice, but you can, if you have an increase in your upstream pressure, you pack that mass into a smaller volume, you get more mass flow. However, a decrease in the downstream pressure does not affect the upstream volume intake, so no change in mass flow. Yes. Yes. Yep. So there, like you can have flow go backwards in a tube, but it's always upstream to downstream. Flow never travels from a lower pressure to a higher pressure. It always travels from a higher pressure to lower pressure. Therefore, I just use the terminology upstream and downstream. Yes. Okay. Like this equation can be used for choked and non-choked conditions, but it's for any compressible flow. All right, Fano flow. So Fano flow, I won't get into the specific details. You'll learn about it more in compressible flow if you ever do take it. However, essentially the way you can understand Fano flow is there is a pressure drop in your system. That is the starting point which we have dictated before. And since there's a pressure drop in your system, well, let's okay, pressure drop in the system, you also have a mass flow in your system. If you learn in aerodynamics, you learn continuity, right? If you have a steady flow, mass flow at one point in your system will always be equal to mass flow in the other point in your system if it's a closed system. So if you have a tube and you have high pressure here with the mass flow, you will have lower pressure here with the same mass flow. If you have the same mass flow at a lower pressure means a higher volume, PV equals MRT. Higher volume dictates that your flow must accelerate. So Fano flow gets into the details and the actual equations for how to calculate how much your flow accelerates due to a pressure drop. Or the other way around, depending on how you want to solve it. I've linked the CompFlow PDF for calculating Fano flow equations if you're interested. And a very big point is Fano flow uses a fanning friction factor. It's similar to the Darcy friction factor. It's often considered to be 4 times less than the Darcy friction factor. You do have to be careful about what factor you use. I recommend researching beforehand what number to use, but understand they are different numbers. All right, putting it all together. So what Fano flow does is it allows you to attain the pressure, temperature, and density at a length downstream of that tube. When you combine that with the previous equation, this one, you can get the mass flow over the entire system. However, this equation is not analytically solvable. Unlike the previous compressible or incompressible flow equations, which are solved using the fluids library, this problem is not analytically solvable. For that reason, you have to use a trial and error solver in order to get the mass flow of a compressible flow system. We currently do not have the code to do this, but if you're interested in getting the code to do this, you can make it yourself. We are interested in this code. I will be developing it sometime in the future. However, if you want to beat me to it, I welcome you because it would be a fun project. You can put it on a resume, put it on a portfolio. And there's no, as far as I know, open source code to do this online at the moment. So it'd be a fun project to take on. Now we get on to measurement. So that's all calculations. How do you measure it? And measurement, I argue, is more important than calculations because you can't verify anything. And measurements you can use to tweak your system to achieve your target values. And often your calculations might vary wildly. So direct measurements are flow meter. That's an obvious one. You can use a flow meter. Different types of flow meters measure different types of flow rates. Some measure volumetric flow, some measure flow velocity, some measure pure mass flow, or other measurements. Tank level, so you can measure the fluid level inside a tank. So you can see, okay, it's at this height at the start of the test, at this height at the end of the test. I knew how long my test is. I can get the mass flow from that. Alternately, for a gas, you can say I have this pressure in my tank before the test. I have this pressure in my tank after the test. PV equals MRT to get mass flow. Last is fluid output. So one can have a bucket that collects all the fluid at the end, and you can see how much fluid traveled through the system through the test. Indirect measurements. So these ones do not use any measurement of the flow itself, but rather conditions of the flow. So there are pressure drops. So you already know the pressure drop from start to the end. However, there are interim pressure drops. So pressure drops across individual fittings or individual tubes. Using those individual pressure drops, if you know the conditions of the flow before and after, pressure, temperature, then you can calculate the mass flow over that one segment. And because continuity, you can say that's the mass flow over the entire system. And I guess I just said that was segmented calculation, but segmented calculations, maybe I could combine them into one. But segmented calculations is that what I just said, you know the flow conditions before and after, you can calculate the mass flow over that one fitting and therefore over the entire system. All right, this is an example problem from a recent cold flow test. So we cold flew the igniter, past tense of cold flow. And this was our data that we gathered. So there's a few things we did estimate. For example, the outlet CD, I used a paper online to estimate that CD. But using these parameters, so the pressure inside the chamber, ambient pressure, you can find the flow rates out of the igniter. So common mistakes, note that PSI gauge must be converted to absolute for mass flow measurements. This was a fun one. It just uses the compressible flow equations as it is air. All right, conclusions. So CV, CD, and K, these you'll see a lot. It is important to know the differences, where they use, where they are not used. And the two different types of fluids. So incompressible fluids and compressible fluids, this is how we calculate pressure drop for both of those. For tubes, Darcy-Weisbach. For fittings, you use the fluids library. For compressible fluids, Fano flow for tubes, and that other equation for fittings. Those 4 equations, actually. All right, are there any questions? Okay, that's it. There, I've got additional references here. Well, not that far. So chemical process safety. This is a book that has a lot of different K values in it for various fittings. That was a useful one I use all the time. It also has various other things which are very useful. And then fluids library. So, all right, no questions? All right, that's it. I appreciate you all for coming. That was a quick 22 minutes. So if you all have any questions about mass flow or anything like that, feel free to ask me. I'm going to upload this PowerPoint online, and that'll be it. Thank you. All right.